You're on, Jeff.
Well, thank you. Thanks everybody for joining the Informix Tech Talk. We'll be talking about Informix SQL performance tuning today. I've been working with Informix for about 30 years, so quite a while. Enjoyed working with Informix product. I'm a IBM business partner that specializes with Informix, and I'm here to talk today about Informix SQL performance tuning tips. This is kind of one of my things that I specialize and like to work on is tuning SQLs. I think it gives you the best bang for the buck with tuning Informix. Informix SQL performance tuning tips. As just kind of gave you an introduction myself, here's my information and the overview. We're going to be talking about identifying problem SQL statements, tracing SQL in Informix, options available with set explain and reading explain output with tuning examples, and methods to use for improving SQL performance. Identifying problem SQL statements. First, you have to identify what SQL statements are the culprits in causing your performance issues. Some of the things that I've used to identify that is using onstat-g NTT to identify the last time read or writes occurred. Another thing is to gather slow SQL statements from onstats, Informix HQ, and third-party tools like Server Studio. Look at how many times SQL statements have been executed using SQL Statement Cache. Another thing is to use the Informix tracing features, the SQL trace. You can look to see how many seconds the SQL takes to run. Review with your developers known problem areas in the application. There's a lot of times where sometimes the developers don't write the best SQL statements, and you can help teach them ways to write better SQL. Verify update statistics are correct. Again, I've saw a lot of times where people have kind of like, oh, we need to run those. So they can also have a big impact in helping your performance. And review what tables and indexes have the most reads. Sometimes if the SQL is not optimized, right, you may have a table that has a high number of reads, but it's mostly due to not having the best indexes out there. So we're going to talk about here, use SQL Statement Cache. You run to see that, you can run the statement onstat-g SSC. Look at SQLs with a large number of executions. Saving even a second on an SQL statement that's executed 1 million times can make a difference in performance. And there's some new features with 1410 for the statement cache that we'll talk about also. Here's a output of the SQL statement cache. It shows a statement cache summary, the size of the statement cache. Gives you the information as far as the SQL statements that are being ran. And for example, here, if I highlight down here toward the bottom, which is 6244, that's the number of times the SQL statement's been executed. So this is where you can kind of go look and say, well, hey, let me take a look at this statement to see if we can improve the performance of that. Some of the statement cache enhancements. There's a new sysmaster table called SSCELM pseudo table to coincide with onstat-g SSC. For more information, you can look at the sysmaster database. There's also an option now that you can invalidate specific statements from the statement cache. And you can also now lock query plans in the statement cache, so that if you wanted to have a certain query plan, instead of it maybe changing due to data, you can lock that. There's dump query plans for the statement cache. There's new parameters, config parameters, statement cache query plan where you can enable or disable. It's disabled by default. It will consume more of your SQL cache size, so you need to make sure you have enough virtual memory to handle that. And the query plan is now viewable in the SysMaster SSCELEM query plan column. Review the number of reads on a table index. Use a sysptprof to look at the buffer reads, page reads, sequential scans. This is one of the tables I look at a lot on systems. So here's kind of a simple select. Select the table name, the buffer reads, the page reads, the IS reads, the sequential scans from the sysptprof table. And you can order it based on whatever criteria you want to look at. And here, this case, I'm ordering it by buffer reads descending, so I want to see the highest number of buffer reads. Here's an example from looking at that information from the previous SQL statement. This one client I was seeing some of their tables or indexes have been wrapped around. So you see the minus numbers on there. That means it wrapped around the counter. So I said, let me take a look at these tables and indexes and see what could be done to help improve it. In this case, by looking at the query and the table and the indexes, recommended using a new index. So after adding a new index, the number of buffer reads dropped dramatically for the table and the index. So it makes it more efficient that you're not just scanning a large amount of data. Even if it's in buffers, you're still going to cost you time and how long the SQL takes to run. Tracing SQL or Informix. There's more ways to find information in tune in Informix utilizing this tracing of SQL. You can do it by setting the onConfig parameter, SQL trace. You can also do it from the SQL admin API, and now with Informix HQ also. So here's the onConfig parameter, SQL trace. You have a level of off, low, medium, and high. The end traces is how many traces that you're going to keep in memory. Again, the SQL trace uses your virtual memory, so again, you need to have enough virtual memory to store this. The size of each trace buffer in KB, and then the mode, either global or user. So here's an example below. We're setting the SQL trace level of low with 1,000 traces, size of 2K in the mode of global. So this allows me to trace the last 1,000 SQL statements of the instance. And with the SQL trace, it's once you fill up that 1,000, it'll then go back and overwrite the oldest ones. So it doesn't grow, it stays at the same size based on the number of traces. And then also with Informix HQ, you can also monitor the SQL tracing. So to improve SQL tracing with the SQL admin API, you can also do it dynamic, set it dynamically when the database is running, so you don't have to shut it down and change the onConfig parameter. So you can set the SQL tracing by adding a database, clearing it, listing it, or removing a database. You can also suspend and resume all tracing the server without deallocating the resources at any time by setting set SQL trace to suspend or resume. Here's how you enable SQL tracing through the sysadmin database by running the following command: execute function task, and say set SQL tracing on, the number of traces, the size of the trace buffer, low or high, and then global. To validate that you can see that SQL tracing is turned on, you can run onstat-g HIS. This prints out information about the SQL trace configuration parameter. And here's an example when you run the onstat-g HIS. The first information again shows your trace level, your trace mode, number of traces, the current statement ID, trace buffer size, duration of your buffer, again meaning how many seconds that these SQLs are stored in the trace buffer. And here's also the output from the onstat-g HIS. It shows the statements, your select statements, and then it shows up down here your costs, estimated rows, your number of rows. Shows the session ID, the user ID, the statement type, when the SQL finished, and then the runtime of the SQL. And there's more statistics that show the number of page reads, your buffer reads, your read cache, your lock requests, lock waits, disk sorts, memory sorts. A lot of information that you can gather from the SQL to better tune the SQL. It shows if there's SQL error or ISAM error, if there was any errors that occurred. You could also get information on tracing through the SysSQL trace table in the SysMaster database. Here's an example of a query to see for how many SQLs take longer than 2 seconds to run. So it says select count from SysSQL trace, where the SQL total time is greater than 2. Another useful table is the SysSQL trace _ ITER, which gives information in the form of an iteration tree for each SQL. It allows you to identify which part of the query plan took the most time to run. You can run the following SQL statement to get the SQL for the ones that have the higher runtime than greater than seconds. So again, in this case, I'm selecting the SQL runtime and the SQL statements where the SQL runtime is greater than half a second, and ordering it by the longest running query. Here's what the SysSQL trace table looks like. There's many columns in here, so you can kind of pick and choose which columns you want that's going to work best for you in finding out what SQLs can be tuned and so forth. So you have the SQL ID, which is a unique identifier for each row coming in. Your session ID, the user ID, the statement type, and here too means select. Your finish time, begin time, your run time, your number of page reads, your buffer reads. And again, a lot more information, lock information, sorting information. Gives you the number of executions, the total runtime of the query. Down here, it also gives information if there's any SQL errors, the amount of SQL memory that it took, which database it was from, the actual SQL statements, whether it used PDQ or not. So there's a lot of information in here that you can slice and dice for your use. You can also save the history of the SQL tracing information. Note of caution, when using this, it can use up a lot of space very quickly. I had a customer, I tried this years ago when it kind of first came out, and we filled a 20 gig DB space in 24 hours. So in the scheduler, there's a new task called Save SQL Trace, which comes in by default, where you can set this. Information saved in the following tables in the sysadmin database: command, SysSQL trace, which stores the SQL statement, text, and profile information. The mon-SysSQL trace underscore info, which stores the statement tracing and setup info. And the mon-SQL trace iter, which stores the statement iterations. Here's an alternative to saving all trace information, because you're not going to care really about statements that maybe take 0.0001 seconds to run. Maybe you want to just look at ones that are greater than 10 seconds. So I created a task which would save the SQL trace information from the SQLs that have run time greater than 10 seconds. So basically, I just took the existing default one that comes with Informix. I just copied that task and created a new one. So this allows you to still trace SQL statements, but only show the really long running statements that you want to look to capture. So you're going to capture 50 instead of 500,000. So here, for example, is creating a new table. Recommend putting it into its own DB space so that it doesn't cause any issues with other tables of filling up. So here's to create table statements with the columns that I wanted to capture, and then some indexes to allow it to be quicker when I'm searching for it. Here's the information needed to be inserted into the PH task table to activate the task. In my case, I was running it every minute. You'll want to see what's the shortest time that your trace buffer is and make that frequency task run smaller than that. So when you first run your onstat-UHIS, it shows how long, how many seconds the trace buffer is. So let's say if it's 100 seconds, you maybe want to have this run every 60 seconds just to make sure you're capturing everything. And here's the SQL, the unload file that you would load into the PH task table to activate this. Using Informix HQ to look at sessions information to see long-running SQLs. Here's just a little example. You can look at the slowest SQL statements, gives you SQL statements, and then some of the information about that. We'll also look at the session information in Informix HQ. You can get information about I/O wait time, CPU time, when it was connected, how much memory it's using, what's the I/O wait time. So again, different avenues to look at your SQL information for improved performance. Now we're going to go on the topic of options available with SQ Explain. Using optimizer directives, avoid execute. So if you have a query, we want to generate a query plan without executing SQL, it's useful for getting query plans for insert, updates, and deletes where data is manipulated, but you don't want to change the data. So if you run the set explain on, avoid execute, and then run the SQL statement, you'll still get the explain plan, but it won't execute that information. Set explain enhancements. You can now turn on and off explain statistics through the config parameter explain_stat. 0 disables it, 1 enables it. You can also set it with following statement, set explain statistics. When it's enabled, the inclusion of the query statistics section in the explain output file. It shows you the query plan's estimated number of rows and the actual number of rows returned. Again, this will help you get more information about your query to better tune it. So here's an example. Doing a select statement. Here's the query statistics. on the table, and here it's showing it was a pretty quick query, 0 seconds, how many rows it was scanned, the estimated rows, and the rows in the database. You can also dynamically set explain on for a running session. So to do that, you execute the command on mode dash capital Y, the session ID, and 0 for off and 1 for on. The output is sent to a file called sqexplain.out and the session ID. With Informix 11, there was a couple of changes that were made. An additional value of 2 to set explain without statistics for a session, display query only plan. Also, you can specify the file and directory that you want the explain output to be sent to. So in case here, you'd say on mode dash capital Y, your session ID, and the file name. It's a great feature to allow you to see SQL statements executed and the explain plan for each SQL statement. Now, to make sure that you only have this turned on for a short period of time because it will create a large file. So you don't want to have this running constantly. And also, can cause some performance issues if you leave this on all the time. You add the set explain on before the statement you want to examine. You can specify, again, the directory that you want the file to go to, set explain file to a file name. By default, it'll put it in the directory that you run the query from. In Windows, you look for a file called username.out in the directory of the SQL explain. So in the explain output, you have your query, which displays the executed query and indicates whether set optimization was set to high or low. It also will show if any directives were followed, and it lists those directives in the query. It gives an estimated cost, which is an estimated of the amount of work time for the query. The number doesn't translate into actual number of seconds. It's kind of useful for comparison queries of the same. And then you also have the estimate the number of rows returned, estimate on the rows returned based on the information from the system catalog tables. Again, another reason to make sure your update statistics are correct. It has numbered list, which is the order in which the tables are accessed, followed by the access method, either index or SQL scan. The index keys shows a column used as filters or indexes, and the query statistics enabled by the onConfig parameter explain stat. Here's going to be some examples of explain plans that we'll go through. Following slides will show tuning of SQL based on the following scenarios: functions causing an index not to be used, criteria from views causing sequential scans, using in clause and sequential scans, use of directives, use of subqueries and queries, substrings and queries, use of functions and queries, and use of a better index. So here's a SQL where a function caused an index not to be used. So in this SQL, we're selecting from a view, and in that we're using an upper for the invoice ID to see if it's like an upper of a value. And in here, there's just performing a sequential scan on the table, even though there's an index on the invoice ID. So what would we do to improve that? Using the upper function can cause it to not use the index. So in this case, we were able to look at the data, and all the data was in uppercase. So we didn't need to actually use the upper function. So when we took that out and just did the and invoice ID is like Kurt, it was now using the correct index. So we see now we have the column business unit and invoice ID, and there's the index it's using for it. Another way is to add a function which converts a character to all uppercase and change the index to include the use of the function. So here we would create a function to uppercase the data, return that all in uppercase, and then create an index which would use that function with the column so that it would be able to, again, get the query back much quicker. So again, two different ways that you can attack the issue. Criteria used to select reviews causing sequential scans. Again, here we're doing a select statement, and looking at the query, I'm like, well, it should be using the index because there were indexes on these columns, business unit, item ID, and so forth. But it wasn't working. It kept giving sequential scans. So I kind of dug into the query. What I'd like to do sometimes is start commenting out parts of the where clause until it actually comes back with a quicker time. So in this case, it's worked out. The first one I went ahead and commented out was the end on quantity on hand is greater than 0. When I commented that out, boom, it started using index. It's like, wow, why would that happen to be a quantity on hand? So we looked at it closer, looked at the view. It was actually doing a calculation for that value, the quantity on hand, which was causing the sequential scan. Let me go back here. Sorry about that. So in this case, we were actually able to comment out the quantity on hand in the query, and we had logic in the program to do the calculations. So in this case, this query went from 20 minutes down to 1 second by doing that. Using an in clause for sequential scans. So in another case here where they're selecting a value and checking if it was in any of these three columns, and it was causing a sequential scan to happen on that. So the resolution was I first created new indexes on 2 of the columns that didn't have indexes in the query. I then changed the query to use an or instead of an in. So here's a case where I changed where and I did an or clause, and now each of these columns have their own indexes, and now we're doing index scans on that select statement. Again, you kind of have to take apart this query and to look to see what the best way to get it to work is. So now we'll come down with less than 0.24 seconds. Use of directives for a query. Sometimes when you look at a query, you try to tune it, and it just won't cooperate. You're like, come on, I need you to go in this order, and it just won't do it. So the use of directives can help you with that. So here's the original SQL statement. For example, here's the cost was $57,000. Here's, again, it's not going in the order of the columns that I want to. So again, that's why it's causing the data to come back slowly. So when I change it to do an ordered directive, meaning I want in the from clause, the tables to be scanned in that order, I then now came back with the query. The cost was higher, but than the original one, but the query came back much quicker. So here we're now filtering because we're going after a single date. So before the explain output, it was going, the criteria for the date was actually down like the sixth criteria. So by doing the order directive, we now were able to eliminate a lot of the data in the first scan, making the query go much quicker. Use of substrings and the best index not used. Again, another type of operation substring can cause programs to do sequential scans or cause a different index to be used. So in this case, again, this query is running slow. The criteria was in the filter. So it was going after just the business unit. And in this case, there was only one business unit for all the rows. So that wasn't very efficient by having the index scan all the rows. So I changed it was to use the accounts did a matches on the column and in order with those three. By doing that, now we're using the account number, the business unit, production value, and account number index, which again returns a query much quicker. And again, another use of functions in a query cause a specific index to not be used. In this query, we were looking for just 1 day's worth of data. But they were using the extend function, which caused the index to not be used. So in this case, this query would take 20 minutes to run. It would run like every morning. But they're like, can't we get this thing to run faster? It's only going after a day's data, but we can't get it to run any faster. So in looking at it, again, we had the filter, the extend, date time. But the thing was, it was searching then for the purchase type codes, and with these purchase type codes, again, it was most of the data. So you're scanning most of the table to get, and then filter just the date out. So what do we do to resolve that? Again, we got rid of the function and we changed the query to do a greater than the current date and less than the previous date. And the cost went down to 2. Original cost was $546,000. And the query went from running in 20 minutes down to like 10 seconds. And here is the index now that was being used for this. So the first column is the time stamp. So that one, since we're going after the single day, that's eliminating most of the data. Here's again another query using a better index. So in this case, we're selecting from the order detail, where again, the date range, its query looks good. When we're looking at the data, it's using a filter. So it's going after the purchase types code, again, which has a large number of data, large number of rows in the table for that column. So what do we do after adding an index? query now came to estimated 3. So again, we had the index for the create TS table, which again, we're going after only a couple of days of data. So that's kind of how you have to look at some of the SQL, saying how are these SQLs being ran and how can we eliminate the most amount of data being scanned initially. Subquery. So I've saw this a lot of times, a lot of clients also. We're doing a select from a table where here's a date range and we're looking for a document number that is in another table. So here, for each record, we're scanning this and then we're looking for the document number and we're going to have to do a select from the documents from the rev table for our document num, where the RE opt ID equals John Smith. So this actually takes longer because of this subquery. So how can we optimize that? The quickest and easiest way is the column that you're doing the in clause, add that join to this column in here, where you select distinct or doc num. When you have that, the query comes back much quicker because you're not scanning everything for John Smith, you're scanning it for John Smith and that specific document number. So that improves performance tremendously. And I've saw this at pretty much every client I've been at. They've had some type of query like this. Next is methods for improving SQL performance. Talk about using multi-index scans, utilizing temp tables when having a large in clause, utilize PDQ priority, and utilize DS9 PDQ query method. So with multi-index scans, if you have a query that has multiple criteria in the where clause, and you have indexes with those columns, the optimizer can utilize multiple indexes at once to improve performance of the query. So here's a case where we're selecting from a table, and we have where this value equals this, or, and then an and clause. So when I run this set explain on it, it's showing we're getting a sequential scan. So then I start to look for, okay, which one of these columns have indexes on them? Let me go back here a second. So when I first run the query, it takes about 3 seconds to run. Not horribly, but if you're running it quite often, it's going to take a while. So here's the current indexes on the table. And when we looked at the actual table to see which indexes have it, oh, we see here, there's one column that does not have an index. So we went ahead and added the index on that column. There's that index. And now you're getting an index scan on this instead of sequential scan. Here's the rest of it. So again, you have to utilize it, set explain on to look at your query plans and to see how best you can optimize or improve your queries, adding indexes, changing the queries, etc. And then here now, so 3 seconds, it took 0.02 seconds for that query to run. Much quicker. Here's a case where utilizing temp tables with in clause for selects. I've saw this many times where if you're doing a select from a table or a column is in, and then you have a long in string, that it can be slower than if you put it into those columns into a temp table and then join the temp table to the original table. So in this case, running this query, it's using the index, but because of the way it has to parse this out, it takes longer. In this case, it took like 18 seconds. Here's utilizing the temp table, we're just loading it into the temp table. Shows the index, we create an index on the temp table, ran the statistics on the temp table, and ran the select the data was in the test. And the query came back in 0.04 seconds. Much quicker. Utilizing temp tables within clauses. Here's again, the query comes back. Utilizing PDQ priority. PDQ is good to be used in creating indexes, but also good to be used for more DSS type queries where you're scanning a lot of data and you have fragments, fragmented tables. So here's a query where we're doing a select on a table, with a where clause. And here you can see when you set PDQ priority, it's showing you can use a maximum of 3 threads. So it can run in parallel 3 operations to get you the data back quicker. Utilizing non-PDQ query mount. This is one parameter that I like a lot when they first came out with it. Is that how do you improve queries for normal OLTP type queries? By setting the DS non-PDQ query mount, you can actually, instead of when you're doing the selecting of the data and doing some sorting, instead of that sorting being done in the temp space, you can have that sorting being done in memory, which is much quicker. So here's a case where it shows I have DS non-PDQ query mount set to 50,000. Here's where this in the stat-GSES information shows how much sort memory buffer is being used. And if I increased it to a larger value, it's using more of the memory. Now, in one case, I got a client, by increasing the DS non-PDQ query mount, and initially it was just set to 128, I set to 50,000. There had a query that went from 2.5 seconds down to 0.25 seconds. And this query was optimized, the correct index was being used and so forth, but by setting the DS non-PDQ query memory to a higher amount, it was actually able to do it in memory. Also, the wait on I/O from top went from 2% to basically 0. So it made a big improvement. One thing with the DS non-PDQ mem is that when you set it, you have to have, it can be 25% of what your DS total memory is set to. And that's it. So in summary, identify problem SQL statements, tracing SQL and Informix, options available with set explain in reading SQL explain output tuning examples, and methods used for improving SQL performance. Any questions? Yeah, thank you.